Hello and welcome back to another episode of Math with Sohn. Today we're going to continue our physics, AP Physics 1, with two-dimensional kinematics. So this first one, today we are going to be dealing with if the velocity is perfectly horizontal. Perfectly horizontal. In the next video, we're going to deal with what if the horizontal velocity is at an angle. Okay, so today is all about with the horizontal velocity being perfectly horizontal. Okay, so with both of that, no matter what, with 2D kinematics, you need to deal with the x component and the y component completely separately. The first question is, how fast is the crate traveling horizontally as it falls? Well, that would be just 120 meters per second. So let's see if I can squeeze that in there, 120 meters per second. And how long does it take for it to hit the ground? Well, it doesn't matter that this is traveling at 120 meters per second. It is in the air 300 meters. This plane is flying in the air 300 meters. That 120 does not influence how long it takes to hit the ground at all. At all. Okay? So with that in mind, we would need to do for part B, we would need to look at our kinematic equations and determine which one we would like the most. So I'm going to show you which ones I use. All right, I use these equations right here on my phone. Which one would deal with only the height? It wants to know how long does it take for the crate to hit the ground. So we have to know a delta x, and we would have to have an acceleration, and we would need to have a t. It feels like it's going to be the second one right here, and I'm going to subtract the x sub 0 over, giving us delta x, or in this case delta y, because we want the height, will equal v0t plus 1/2 at squared. So would equal v0t plus 1/2 at squared. Well, the initial velocity, it's not being thrown down with any velocity, so this part's going to cancel out. We know that the change in y direction is going to be negative 300 because it started up here and it went down by 300. Will equal 1/2 a, which is the acceleration due to gravity, negative 9.8, times t squared. We just solved for t at this point. We would multiply the 1/2 and the 9.8, 0.5 times 9.8, I don't even know I'm using a calculator for that, is negative 300 equals negative 4.9 t squared. A lot of you might have just memorized the negative 4.9 part. 300 divided by 4.9 gives us, because they're both negative, a positive 61.22 equals t squared. If you square root that, square root of that, you get the time for part B is equal to 7.82. Okay? So part B, we know the time it hits the ground, which is very, very important. If we didn't know the time it hit the ground, seconds, then we probably wouldn't be able to do anything else. So how far horizontally from where it is realized, or where it begins, does the crate hit the ground? Well, now that we know the time that it was in the air during this entire 120 meters per second, it never slows down. You have to assume that air resistance is negligible. So for part C, we have it being in the air for 7.82 seconds, and every second it is in the air for, it is going to be moving at 120 meters per second. So with that in mind, you could again use the delta x equals v sub 0 times t plus 1/2 at squared. Well, there's no acceleration in the x department. It is just moving 120 meters per second to the right, so that part cancels. And your change in x, which was what we're looking for, is equal to our initial velocity, 120 meters per second, times 7.82 seconds. Well, the seconds would cancel, leaving us with 120 times 7.82, which is a change in x of 120 times 7.82, 938.4 meters. Okay? So that kind of makes sense too. It's really just if it's traveling 120 meters every second it's in the air, well, you would just multiply 120 times 7.82. Part C, done. What is the crate's velocity immediately before it hits the ground? Okay. Well, that part would take a little bit more effort because the crate's velocity is going to involve two different things. It is moving 120 meters per second to the right. but it's also moving down due to gravity. And both of those are going to influence its real velocity because it's not going to the ground to the right like 120 meters and then down 300 meters. It's going to the right and down simultaneously, and it's going to follow this sort of motion when it's landing. So we need to figure out essentially this hypotenuse velocity. And in order to find the hypotenuse of that, we need to find the x component and the y component, which we just found the x component. We already knew the y component, and we need to figure out the velocities of each. So the 120 meters per second is going to be constant. We need to figure out the y component. Even though it has 300 meters, we don't know the y component for velocity at that moment. So let's do that. We got v, for part D, v equals v sub 0 plus a times t. Well, v sub 0 for y is 0 because it didn't start with any initial velocity. So that part cancels. Your y velocity would equal the acceleration due to gravity, negative 9.8, times time, which is 7.82. And if we do that, we get 9.8 times 7.82. We get the y velocity is going down at negative 76.63. That would be in meters per second. So we have the x component and the y component now. How are we going to figure out what the actual final velocity is? Well, I said it's the hypotenuse. We got 120 meters per second here. We got 76.63 meters per second there. We need to do the Pythagorean theorem. So we got 120 squared plus what we just found here, which is technically negative 76.63 squared. And that would equal your final velocity squared. So 120 squared plus that squared, you would end up square rooting it. If you square root it, you would get 120 squared plus 76.63 squared. You would get approximately negative 143 meters per second. Okay? Now, if we wanted to know the angle that it was making right here with the ground or right here with that part, because the angle of elevation and the angle of depression are the same thing according to geometry, you would have to use inverse trigonometry to figure that out. And you could, by doing tan negative 1 opposite 77 over adjacent 120, tan negative 1 opposite over adjacent would give us an angle of 33 degrees when it hits the ground. So it is producing that angle of elevation / depression. They mean the same thing with it when it hits the ground at 33 degrees. All right. All that being said, that's going to do it for this one. In the next episode, we are going to take this horizontal and vertical component and deal with that angle, because not everything is going to go straight to the right when it's being launched. Many things are going to be launched at an angle. And if they're launched at an angle, we will have to utilize that to figure out the x and the y component and how that affects both the vertical and the horizontal velocities. Until next time, stay positive, my friends, and I will see everybody later. Bye.